Let's start with the equation 2x plus 1 equals x. To solve, we square both sides of the solution to get 2x plus 1 equals x squared minus 2x minus 1 equals 0. We solve for the roots using the quadratic equation. 2 plus or minus the square root of 4 minus 4 times negative 1. That makes it plus 4 over 2 equals 2 plus or minus 2 radical 2 over 2 equals 1 plus or minus radical 2. So we have two possible solutions. Not all of these solutions work, and let me show you. So let's take 1 minus radical 2. That equals radical 3 minus 2 radical 2. Want or need to compute this, but I can conclude that this number is greater than 0. And that's because radical 2 is approximately 1.4. So 3 is greater than 2 times that. However, 1 minus radical 2 is definitely less than 0. So this quantity, 1 minus radical 2, is not a solution. Not a solution. So what went wrong? That is the question I want to address with the rest of this lecture. Okay, so let's backtrack and go to the origin. Which step here, from here to here, from here to here, or the computation of these roots, which step could there possibly have been an error or something that gave us the non-solution? The step is this one. It's not incorrect to do it, but it gives us more solutions than truly exist. And let me show you why. A simpler problem to illustrate. Let's look at 2x minus 1 equals x. This is very easy to solve. The answer is x equals 1. You can see this algebraically as well as graphically. The graphical question is, we've got the line y equals 2x minus 1. Where does it intersect the line y equals x? And those two lines intersect at x equals 1. Now suppose I squared both sides of this equation. 2x minus 1 squared equals x squared. What do I do to my original equation? I turn it into a quadratic equation. Specifically, the equation 3x squared minus 4x plus 1 equals 0. And that factors into 3x minus 1 times x minus 1. We see that x is 1 or 1/3. Now, notice that one of the solutions matches the x equals 1 solution. why do we have the 1/3? First of all, does 1/3 work? 2 times 1/3 minus 1. Does that equal 1/3? No, because this equals negative 1/3. So this is not a solution to the original equation. So what just happened? What happened is that we turned this linear equation, this line equals this line, into this quadratic equation. This parabola equals this parabola. Where does this parabola equal this parabola? Which generally has two solutions. So to show you graphically what's going on, we're going to plot these functions. Here you see the two quadratic functions, x squared and 2x minus 1 squared. And you see that they have 2 points of intersection at 1 and 1/3. Now let's take a look at 2x minus 1 and x. They only intersect at 1. Let's show them all at once. You'll see that 1, x equals 1, y equals 1 is the point of intersection of all the curves. Now let's go back to our original problem. We did the same thing from this step to this step. We squared both sides of the equation, turning this problem into a different problem, into a quadratic problem, which has two real solutions in this case. So what's the moral of the story? The moral of the story is that if you have a of x equals b of x, and you square both sides, you will in general not get the same solutions, because this process of squaring both sides of an equation introduces more solutions, specifically because if a equals b, negative a x squared equals bx squared. So what you will often get is that the solutions will differ by a sign. So in this case, notice that if you plug in the wrong solution, 1/3, into the original equation, the two sides differ by a sign. And let's go back to our very original problem. You'll find that these two numbers also differ just by a sign. Here we plot the original equation, radical 2x plus 1 and x. Where does it intersect? At the point 1 plus radical 2. Now notice if we plot the parabola we get when we square both sides of this equation, radical 2x plus 1 equals x, that one of the zeros indeed occurs at 1 plus radical 2. But how about the other 0 at 1 minus radical 2? Here's the other 0. That is not where the blue and the red curve intersect. However, as I said, the difference is just a sign away from each other. So it is where the blue curve intersects with negative radical 2x plus 1. So you can see it algebraically here. I compute radical 2 times 1 minus square root of 2 plus 1, and I get 0.4142, blah, blah, blah. And how does that differ from 1 minus radical 2? Just by a sign. Just by a sign. And then this computation shows that indeed 1 plus radical 2 is a solution of the original equation. These exercises show is that this equation is not equivalent to this one. In other words, you will get different solutions, different values of x. And in general, this equation is not equivalent to this equation, where O is just some operation. Unless that operation is invertible. So, as an example, ax plus 5 equals bx plus 5 is equivalent to ax equals bx. Why? Because if you find a solution to this equality, you can simply subtract 5 to get here back. Here we show why the square root is not exactly the inverse of squaring. In other words, how squaring is not invertible. If we take the square root of negative square root of 2 squared, we get the square root of 2, which is not equal to the original argument that was being squared, which was negative square root of 2. This concludes our exposition of some of the subtleties that come up when you are solving equations for x.